I hope somehow this screen is gone. Is it okay? I just click the...
Just click the start. It will start recording.
This one is gone.
Oh yeah, it's okay.
Is it okay?
Check.
Is this gone?
Oh, yeah.
Okay.
Yeah, it's okay. Yeah.
Hopefully it's okay. Okay, anyway. So this is the lecture for Conformal Symmetry. So I heard both undergrad and graduate students are present here. So, and then, so here first, my plan is to do so Conformal Symmetry. Okay, can you raise your hand? How many of you are undergrad students? Can you raise your hand? Okay. How many of you are graduate students? Please raise your hand. Okay. How many of you are from SIMIS? Nobody from SIMIS. This Shanghai Institute of like blah blah blah. Math Center. Okay, nobody is from. Okay, I heard that this semester there are 2 courses on conformal theory on SIMS. So that's one of the reasons why people do not come. So since repetition is a father of learning, there is some famous idiom in Russia. So if you're interested, then you can go to the SIMS. There is a lecture by Tomoki Nosaka on 2D conformal theory, and Wenjie will give a lecture on higher dimension conformal theory. That's what I heard. But my plan is to do both. So I'm Satoshi. You can call me Satoshi. So my office is Java S422, so you can stop by whenever you want, and then you can ask. So you can ask via WeChat, and then TAA is the Junka. Juan, can you stand up? So he's the TA, so you can ask him if you have some questions, even. Okay, so then, and then the grade is 50% of the homework. Okay, homework set. In total 6, 6 in total. Not so much. Okay, and 50% of final exam. So that's the plan of this course. Any question about grading and so on? Okay, and so my plan is that the first plan of the lecture is first talk about the 2-dimensional conformal theory, and after that go to higher dimension CFT. Yes. So that's what the plan. 2D. So depend on how much we cover, and depending on speed of the lecture, we'll see how much we can cover. But I'm not going to go to so much so fast this time. So let's do one by one. And here it was all lecture note available. Lecture note. Note. And here's I'm going to use a new lecture note. New note. I share my olive. So that's the plan of the lecture. So and then up to section 6. Here, section 6 talk about renormalization group flow and then Zamochka-C theorem. But after that, I will switch to the higher dimension. So that's the plan. But even first part, I will just mix the new lecture note and the first part is the conformal symmetry. So this one we can do both. We can treat both 2D and higher dimension at the same time. So no need to follow the old lecture note. And then after that, we will talk about something about let's see. Yeah, primary field. So field, and then conformal Takahashi, and then we will talk about the universal algebra. So that's the first we will go the basic part, and then from after that I will talk about the flow is some free field number 5 and the minimum one. So that's the in the 2D theory, 2D conformal field theory part, and number 6 is the RG flow renormalization, RG flow, and then lambda is normal, lambda against normal. That's the number 6 of 2-dimensional field theory. So that's the plan of my course. In the first part, hopefully before around April we can finish this one, and then in May we will go to higher dimension. So the rough plan I wrote in the so let's see, wall symmetry, and also conformal symmetry in higher dimension, conformal symmetry in D relevant, and then also example free theory, free scalar in D relevant 2, and also talk about something about representation of conformal algebra. So those are the we are going to talk about, and then a little bit talk about so there is something called operator product expansion. So there's an important concept called operator product expansion. Both sides. So that's the plan, and then here I will talk about a little bit about some example. So for instance, with a picture point, in the renormalization group hole, and then hopefully something about conformal. Block, something related to 3D Ising model. So those are the rough plan of my this lecture. Okay, so that's the last round of my lecture. So, but we will go step by step. Any question at this moment? So why do we need to, what is the conformal symmetry? So what is the conformal symmetry? Conformal symmetry. So somehow it's already well known that my course is difficult and then densely packed. Lots of contents are densely packed, but this time I will try to be slow and pedagogical. So if you have a question, feel free to interrupt me. Yeah, somehow it's well known that I'm a very strict lecturer and supervisor, but you can always ask some questions. Fine. So what is the conformal symmetry? So the conformal symmetry is the first of all the symmetry Euclidean space is the okay. So what is the symmetry Euclidean space? Can you what kind of symmetry Euclidean space has? Speak up. Hmm? What symmetry? Poincare symmetry. So what is Poincare symmetry? It's generated by what? Okay. So translation and rotation depends on. So I'm talking about the Euclidean spacetime, so it's a rotation, or Minkowski is a Relevance symmetry. So these are called Poincare symmetry. Okay. So those are Poincare symmetry, and then another thing we have to add is called so-called scalar symmetry. So here is the usual, okay, as he mentioned, Poincare symmetry, and then so we need to add so-called dilatation or scaling transformation, or dilatation, scaling transformation. So that is the or dilatation, dilatation. Okay. So that is just if you have the triangle, whatever triangle here, and then dilatation is something like that. Scale the size like this. So these are the transformation which conformal symmetry is involved. So if physics is the how to say. So in our lecture, this is clearly not true because we cannot how to say scale up and scale down. But in some physics, you can have this kind of like scaling symmetry. So this is the symmetry. So therefore, so if you have like a preserved angle of the triangle, and then but the angle is preserved, but this length is not preserved for triangle. That is called scaling function. Okay, and then another thing is the let's do the infinite. Let's do the so another thing is inversion symmetry. Inversion transformation, I call it inversion transformation. So this one is just it's just mark. If the x equals to x divided by x, that's the Euclidean space. This is the inversion symmetry. So therefore, if you have the Euclidean space, you have a unit circle like this way. So this is the 1 and 1 and whatever x1 x whatever 2 3 up to D dimension. So therefore, this is the D minus 1 sphere. So this unit sphere, and you have an X here. So you have an X here. So then you just write down the length like this way, okay, and then the vector is scaled by X. The absolute square. So therefore, it just mapped around here. So around here, so that is the X divided by X squared. So this is the inversion with respect to unit circle. So this is the transformation we will include. Okay. So this transformation is just mapped. For instance, okay. So under this transformation, let's see. So I just give you some example. So this line is mapped to where? Under this transformation, this purple line is mapped to where? Under inversion. What is the shape of this under this inversion? Huh? Half circle. Half circle. How do you map to half circle? So this point stay as it is. Okay? But this point is mapped to around here, and so on. This point is mapped to This point is mapped to around here, and so on. And at the end of the day, so the infinity is mapped to origin, right? Infinity is mapped to origin because therefore, at the end of the day, what's happening is that this line is mapped to circle in between this 1 and 0. Okay? And since this line does not include infinity, strictly speaking, you have to get rid of the origin. You have to get rid of origin. Okay? So this inversion transformation is mapped like a line or circle to the itself, circle itself. Fine. Another example I can show is that there are lots of examples one can just consider. So for instance, if you consider the circle something like say, circle like this way. If you have circle like this way, this will be mapped to the so the common, we just common circle like this. This yellow circle is mapped to this purple circle under inversion. So the circle is mapped to either circle or line. That's a property of this transformation. Okay. So now, we just we can consider some composition of the transformation. So the conformal transformation is conformal symmetry is very simple. Essentially, this is the everything what we want. But so there is something called special conformal transformation. So this one is the operation something like this one. So there is a unit circle like this way. Okay. Unit circle like this way, and you start with x around here. Okay. So x around here. And do the inversion again. So if you do the inversion, something like that, it's just mapped around here. This is x and x squared. Okay. And then after that, you just do the translation formulas. So translation is something like a. So therefore, this point is something like a x squared plus a, and do the inversion. And if you do the inversion, the next step is something like this way. So maybe something around here. So this is a new point, x prime. So this special conformal transformation, x is mapped to x squared, and then you just have the translation by a, and then inversion. And then you have square, the same thing. And if you do that, so if you do that, you simplify it, you get this this kind of thing. So so that's the transformation, which is called special conformal transformation. So this is also, I mean, this is just involved inversion and translation. So translation just maps circle to circle with the same radius. So therefore, we don't. So circle to circle, and then so another inversion also represents circle to circle or line. Therefore, so another special conformal transformation, circle is mapped to circle, either circle or line. So that's the how the conformal transformation works. Fine. So that's the generator of a conformal symmetry. It's also a generator of conformal symmetry, so it's a very simple. Any question at this moment? It's very simple so far. Any question at this moment? Okay, so then let's look at the infinitesimal transformation. Infinitesimal transformation for generator of system. So f of x is mapped to f of x plus epsilon. So that's the suppose epsilon is very small. So this is translation. Okay. And do the Taylor expansion. Do the Taylor expansion means the f of x plus epsilon mu. This is the first order for the epsilon. Fine. So therefore, infinitesimal transformation for translation is this guy. This guy. And then up to some convention, I just put the minus I and the partial. This is the generator of the transformation. More precise way of speaking, that this is the vector field that generates the translation, which is the one parameter family of the moment, okay, which is a translation. So if you write down the last picture, so there's a Euclidean space, translation is something, vector field is something like this. Vector field is something like this. So those are your vector field there. Okay, what is a rotation? Rotation is f of x. So this is a translation. F of x is mapped to f of x mu plus epsilon mu x mu. Okay. So epsilon, is it too small? Is it okay? The student at the back, is it visible? Just tell me. You guys can see that. Is it okay? Right side. Okay. So that is. So this is the anti-symmetric tensor. And do the Taylor expansion. So this is f of x. Okay. So So this way is x mu, partial mu, minus m, and 1/2, which is anti-symmetrized and the f1, and the order of each one. Okay. So that's the Taylor expansion. The result of Taylor expansion we get is this one. Okay. Strictly speaking, if this is a plus and this is a minus. Are you guys following? Is it okay? So since if you do the Taylor expansion, the first order is something like x mu, epsilon mu, mu, x mu, mu, so that will come, but you can anti-symmetrize mu indices to get the extra piece like this, and then divide by 1. That will give you this. Therefore, this guy is the generator of rotation. So usually people just write down JB mu. Oh, sorry. With the low indices. Like this way. Like this way. So this is the rotation. So generator of vector field that generates rotation. I mean, this is one of the rotation JB mu is essentially given by like this way, and like this way. I mean, in classical mechanics, the angular momentum is given like this way, x cross p, and then once you go to the quantum mechanics, p is replaced by derivative with respect to x. You get this. It's the same thing. Fine. So what is the scale invariant? Okay, so unfortunately, so this is one by one. Scaling transformation is super easy. So f of x is equal to fx minus epsilon x. So epsilon is just some scalar quantity. And this one is given by f of x mu plus epsilon x mu, sorry, x mu partial mu f of x plus order epsilon squared. So this is a consistent Taylor expansion. Everybody should be familiar with this kind of transformation. So therefore, this guy is a generator. So leading order. So d is equal to x mu partial. Okay. So this is a general dilatation. Dilatation. Okay. Any question at this moment? And then the last is the something called scaling transformation, the special conformal transformation. So if you just look at the A is very small. So for instance, sorry, let's see. Yeah, so if A is very small, so if you look at this one, and then A is very small. So this one is so A is very small. So this one can be written as follows: x mu. Just look at the leading order of A. So this is x mu plus A rho A mu x squared. So this is what you get. I mean, it's very easy. So this is x squared. I mean, do the Taylor expansion for once you treat A is very small. Okay, then this one will give you this times 1 minus 2 times A times x. So that you will get this one as a leading order. And you forget about the subleading order for A. Okay. So from there, one can just conclude that this special transformation, special infinitesimal version, special conformal transformation. You just look at this a part, which is I times minus x squared special mu, and then over that plus 2 x mu x rho partial rho. Okay, so that's what we get. Is it okay? Maybe I should write down this as the minus one. Minus I minus x squared partial. Is there any question at this moment? Is it okay? Is it clear for you guys? Well, so those are infinitesimal transformation of conformal symmetry. So if the system has conformal symmetry, I mean, line and circle treated as it is are the same thing. Also, the triangle with different size treated as treated as the same thing. Fine, and then so once you have this, so we need a conformal algebra. So what is an algebra? Algebra means that we need some multiplication. We know so in the case of the rotation, so it's a good exercise to do. I, J mu, J from sigma is given by the J mu sigma minus delta mu J mu sigma minus delta sigma mu J rho mu delta rho mu J. So this satisfies rotation will satisfy this computational relation. So of course, as you know, so this bracket is the AB minus B. And since you just need to plug in this guy into A and B. Okay? Since derivative C is x, so just acts on non-trivially. Is it okay? Derivative acts on non-trivially. So what's left is something like a proportional to, I mean, essentially x. So some indices are high, like x and sigma. Derivative. So derivative Cx, right? So therefore, essentially the structure is x times rho derivative, partial derivative. Okay, which is inside a J. Okay. But you have to be careful about the indices. So then what at the end of the day you get this computation relation. Okay. So this is the exercise you have to do. It's a tedious, but one can do. Okay, and then another exercise one can do is at the P mu J rho sigma delta. So we just do the same exercise. Plug this guy now upstairs over there. Upstairs over there, and this one, and plug up into here, and you get this one. And then of course, this is equal to what? Phi, good. Since it's just derivative, it's common. So this is the algebra. of conformal symmetry. But now, okay, so this space. So now we have an additional generator, so this D, and also this K. Additional generator, this K. Okay. Additional generator is here. So we just need to consider the following state computational relation. So I just write down a non-trivial thing. This minus AB and D is equal to KA. And then PU is equal to 2 times delta mu D plus 2J. Fine, and I times mu J mu rho is equal to delta mu K rho K state. Sorry, I think my rationale was rho sigma. Sigma minus delta mu sigma K and rho. Okay, so that's direct computation. Just plug that into the ball. Just do a calculation. Do a calculation, you get this. Okay, so let's compare. So this part is very resemble as this guy. Okay, it's very looks like it's very similar. Okay, and also. This guy looks like this guy. Only signs are different. Okay. So the output K and P. So the conclusion, the K and P are very similar. Okay. At the level of algebra. Algebra means this bracket is treated as kind of multiplication. So therefore, algebra means you have addition and then multiplication. So algebra means that you have addition and multiplication. In this case, multiplication is given by like this way. Multiplication is this commutator. So when you do a multiplication, you just scalar multiplication. And multiplication B is really like a multiplication. It's just you just have a like this. You have a multiplication, but in the how to say, the algebra in this of symmetry is that they always A cross B is AB minus B, or namely A commutator. Okay. So algebra means the addition and multiplication, and so this commutation relation is treated as a multiplication. Anyway, so in the algebra, K and P are played a very similar role. Okay. Very similar role. Okay, and then so the other is trivial. Other. But under this so dilatation, you have a different charges. You have a different charge. So this sign is minus and plus. Depending on the convention, P has a -1 charges, K has a +1 charges under dilatation. dependent notation. Alright. Any question at this moment? Okay, so now for translation is very different, look like a very different from the special conformal transformation, which is just take an inverse translation and inverse. But at the level algebra, it plays a very similar role. And further magic will happen once you just improve the point redefinition. Anyways. So this one, you really need to do a calculation. So J which I raised here, is something like d times d. So it's a Euclidean space. I consider Rd space, so the x1 dot xt. The coordinate is given by this one. And the J mu is just given by the one I just erased. J mu. So this is d times d by matrix, d by d matrix. We can add something like the following thing. So this here, I added the minus p mu minus k mu. Okay, maybe we try to make them bigger. To see. P mu plus k mu divided by 2, and then p mu minus k mu divided by 2. So this is the matrix we have, and then J mu, and this is the. Okay, so I mean it depends on how we define it. Okay, I think to define it. Okay, I think I'm very sorry. So I think let's follow my lecture notes honestly. Not make you guys confused. J mu is like this way. Let's do the following way. Without p mu plus k mu divided by 2 is here. Minus p mu plus k mu divided by 2 is here. Okay, so this is the d by d matrix. This is the d by d matrix. This is the d, and this is d. So therefore, this is d plus 1 arrow. This one row and d plus 2 row is here. Then each entry is just given by a combination, linear combination p and k. Okay, like this one. And I call it this one is equal to md plus 1 mu. And this is md plus 2 mu. So here I put the minus of md plus 1 mu minus md plus 2 mu. So I just, since this one is, how to say, is the anti-symmetric matrix. I want to create an anti-symmetric matrix. So therefore, if you take a transpose, it has to be, you get the negative sign. So therefore, this entry should be negative of this entry. Okay? This entry is negative of this entry. Okay? So that's why I put the minus sign here. And then I put that here is the D here and minus D and 0, 0. So I call it this matrix is the M and B. I call it B. Okay. B. So then it turned out that it just gives a very magical thing. So I will erase this part. This part is going to be the following algebra. So I, M and B, M, C, D is equal to delta B and then C, M, and D minus, not delta, sorry, eta. Eta AC, M, BD, BD minus eta, D, B, A, M, C, D plus eta, A, CB and CB. That's what we. Am I writing correctly? Eta BC, eta AC, BD, eta DA, CP. Sorry, there is something strange in my lecture note. What's going on? Sorry, I think there's something wrong in my lecture note. Or, oh yeah, I think this is not correct. Sigma is E and mu is what? Mu is okay. Something strange in my lecture note. Something strange in my lecture note. And this is the sigma mu B and O. O. And the mu is A, sorry, CA. And here is something strange. Okay, so this is not correct. Sigma mu, sorry, sigma mu. Okay, so therefore this should be, BD. Okay. Okay, so my lecture is still okay. So essentially, you just replace J and M, and replace delta and eta, where eta is something like a diagonal. Is 1 minus 1, and how many 1 do you need to have here? How many 1 do you need to have here? Huh? D plus 1, good. D plus 1, and this is 1. Well, D plus 1 plus sign, and then 1 minus sign. Okay? And so therefore this algebra is called SO D plus 1, 1. The algebra. So Conformal Symmetry or Euclidean symmetry is SOD actually. SOD. It's just that's not true. SOD cross R. Maybe I should write that this is translation. But not R. RD. Okay. Yeah. So the SOD is a rotation and translation. And they have non-trivial commutation relation, so I just write that, not the direct product. I just something going on in between these. This is the Euclidean symmetry, but if you included this dilatation and the inversion, you get the SOD plus 1, 1, the algebra. So essentially, it looks like Minkowski symmetry of Minkowski R D plus 1 over 1. Minkowski space of D on D. Okay. Lorentz symmetry. So that's the completeness of this analysis. Any question at this moment? And in fact, if you start with the Minkowski signature, SO D minus 1 over 1. So this is the Minkowski. So this is the Euclidean symmetry to the conformal symmetry. But here it's a Minkowski. And if you go to the conformal symmetry in the Minkowski space RD, so R D minus 1 over 1, and then this is the conformal symmetry. So that's what you get from the analysis. Any questions? Okay. Any questions at this moment? So that's the conformal symmetry we consider. Yeah. So, so there is something called Casimir. Quadratic Casimir. So if you have the So Casimir is in quantum mechanics. You learn that the how to say you have a Jx J, which is essentially x cross p, and then they satisfy this algebra, this kind of algebra, and then the representation. So J and n, which add J squared, is equal to J plus 1, Jm, representation, and then Jz acts on Jm is equal to M Jm, where M runs for J and minus J. Okay, so that's a spin J, it's called spin J representation. Spin J, it depends on how you want half. Anyway, so that's the spin J representation. So this guy is invariant under the rotation. So if you shuffle XYZ, the role of XYZ, this guy is invariant. So this is called for the Casimir. So now called J squared is defined by Jx squared plus Jy squared by Jz squared. So it's called for the Casimir. In the case of this guy, high dimensional conformal symmetry, so whichever is okay. This guy or this guy, whichever is okay. So then Casimir is given by CZ given 1/2 NAE, and which is given by J mu times D squared plus 1/2 K mu. I mean, it depends on, that's that. That's what you get under other generalization. Other generalization of this one. So this is SO3. but SO D minus Dn plus 1 comma 1 or SO D comma 2, you have to use this this guy as a closure guy. So which is invariant in the rotation of the or conformal symmetry. Fine. Any question at this moment? And one comment I have to make. So this is the generic dimension I talk about, but there is something special going on. So the reason why we need to consider, I will go into detail, but later. D equal to 2. D equal to 2 is very special. Very special, as we will see soon. So this one, when you set equal to 2, so this SO3, is enhanced. Universal algebra, infinite dimensional algebra, called Universal algebra, as a quantum mechanical. Or before that, we will see bit algebra, but we will see bit algebra, or whose central extension is called Universal algebra. Anyway, so if you consider conformal field theory, so the Universal algebra is more simple. Okay, so therefore, as we will see so in 2 dimensions, not only SO3, is a symmetry, but also it's just get enhanced. So generator is to the infinite many generator you will see. So here it's just so if you look at this n, it's just D plus 2 by D plus 2 matrix. So therefore, you have a finite many entry you can see. But if you go to 2 dimensions, somehow this D plus 4 by 4 matrix is somehow enhanced to the infinite times infinite. That's not precise, but anyway, so the infinite dimensional generator you see. So that's why this guy is really powerful, and this guy is very powerful. Two-dimensional field somehow is a lot of things under control. Any questions at this moment? Okay, so those are conformal symmetry. The introduction of conformal symmetry. Fine. Why is it important? So now we will talk about why conformal symmetry is important in physics. So that's a question we can ask. So so to explain that, we just need to consider so-called the Ising model. So Ising model is the various Ising model, or which comes now. And then So this is given by Campbell. So this critical phenomenon, universality, to explain critical phenomenon, we say Ising model is the best example we can consider. But before we go to Ising model is just we consider lattice in D dimension. Lattice in D dimension. At each side, we have a spin up and down. Like this. So this is called spin level, and the Hamiltonian is given by the interaction is given by this sum of J. I mean, it's some constant you get. I mean, I don't care if it's constant, to be honest. J, sigma I, sigma J, and I and J are adjacent. So those are the interval I mean, J is usually can be treated as some constant. It's okay, it's a constant. I mean, can be depends on I and J, but it's also important. And if you have an external field, outside the field, you have a H or whatever. Magnetic field, you have a I. I is a site. So I is the living site. 1, 2, 3, 4, and so on. And living site. 5, 6, 7, 8, and so on. This I, the sum indices are just the living site. So this one, and then we can consider the statistical, partition function, which is given by the Z is given by sum of sigma I is equal to plus minus 1, and then you have e to the minus beta h. Okay, so this is statistical partition function. Partition function, or whatever partition function. Okay. Partition function, and you can consider free energy and so on. Okay. So here, beta is of course given by the 1 over dt, and so on. So since that, so physics prefer the energy D, lowest energy. Okay, so therefore, if temperature is very small, some is very small, whatever. Some according to some typical temperature of this system less than very small. The people try to align because then there was some fluctuation. So we just they try to indicate together. So they try to make. So we have if they try to align like this one, and there is no some fluctuation, so they prefer to be steady state. However, this is a low temperature regime. So then, if you change these low temperature, if you go to high temperature regime, okay, thermal fluctuation is very high. Okay, so then it behaves like this way. So okay, so I don't need to write that. So this is T is, it just becomes random. It becomes T is greater than TC. It just becomes random. So it's just thermal fluctuation is very big. So the spin try to behave randomly. Okay. And if you have the magnetization, the sum of magnetization is sum of sigma I is run for I. Therefore, we have a magnetization, and this is temperature T. At the 0 Kelvin, there is no thermal fluctuation. So either they are spin up or spin down. All sides spin up, spin down. Therefore, you start with 1 here, or minus 1. Okay? And once you increase the temperature a little bit, they start a slightly, one of the sides is like sometimes flip, sometimes just go back and so on. So that magnetization just decrease. So at some certain temperature, Tc, magnetization becomes 0. So that is called Curie temperature. So there is something phase transition occurs. So this is the something called phase transition. So before Curie temperature, magnetization is non-trivial. But if you go to the higher, so thermal fluctuation win against the interaction Hamiltonian, interaction term in Hamiltonian, so that it becomes 0. Okay, something. So this Curie temperature, Tc, is called Curie temperature. It's a very interesting point. People are interested in at T equal to Tc is the so very interesting point, and there, so people, there, so here it becomes like a chunk of the, so this is described by so-called conformal symmetry, CFT. It's believed, okay, believed to believe that this T equal to Tc is the so if you look at the for instance correlation function and so on, so it's very so one physical quantity one can consider is that so here we have G of R is something like sigma I, sigma j minus sigma I and sigma j, and this behaves something like this way. Where the R, so this R is the length between I and I minus j. So anyway, so this I point, the correlation correlation function is the sigma I. Is sigma I here and sigma j here. How they interact with each other, correlate with each other. So that's the correlation function one can consider. It's just that this is the statistical average. This bracket means statistical average. You can consider, and this behaves like as follows. So R minus tau and e to the minus R divided by C. So that's the typical behavior of typical behavior of the correlation function will behave. So depends on the so when R is less than C, okay, R is less than C, they start correlating. They start they correlate to each other. So I mean, R is less than C, the typical scale of the, they just try to align. Okay, they try to create a cluster of the same spin. But if you they correlate. But when R is less than, when this R is greater than, on this side, no correlation. Okay, so that's the typical behavior you will see in this kind of statistical system. But t is equal to, so when t is equal to t equals to tc, this correlation length c goes to infinity somewhat. Okay. So therefore, any point will look like a correlating each other when you go to t equals to tc. So c goes to infinity. So therefore, any point is starts correlating each other. So that's the T at the Curie temperature you will see in the physics. So in fact, what's going to happen is as follows. So I think I can show you the video later about this. I think if I use this one after the break, I will show some video. So at T equals TC, there's no notion of scale. There's no notion of scale. So that everything just starts correlating each other. So therefore, if you zoom in and zoom out, all physics look like the same. Physics look like very similar. So therefore, that's why it's the reason why it's believed to be described by conformal filtering, and furthermore, at T equal to Tc, this correlation function Cr is given by R minus D plus 2 minus A, and C is given by T minus Tc and minus E. So that's the people usually look at the and this quantity is called critical exponent. So this A, so this quantity is called critical exponent. So, critical exponent, and then so 2D Ising model, 2D Ising model. So I think the body should be consistent. Yeah. Wait. So for 2D Ising model, so 2D Ising model, so D equal to 2, D equal to 2, eta and then mu are given by the following quantity. Mu is given by 1, and then eta is 1 quarter. D equals 3 is very recent result given by numerical study, or so let's go 0,01, and then mu is equal to 0,61, and so on. So this critical exponent is somewhat characterized CFT. So those are the co-critical exponent, and so on. In fact, most important thing is the so universality means that this critical exponent is independent of the detail, microscopic detail of H Hamiltonian or system. So for instance, here we consider the square lattice. If we consider square lattice, but we can also consider the triangle lattice. We can also consider triangle lattice or whatever lattice one can consider like this way. So one can consider this kind of triangle lattice and so on to consider the Ising model at each lattice. But if you do not change dimension, if you have the same dimension, you get the same value of critical exponent eta and mu. And even if you change J slightly, it doesn't change the critical exponent. And okay. So that's it's called universality. It's called universality means that you don't need to worry about the detail of the theory to see the macroscopic. So this is the macroscopic detail, macroscopic quantity. To know about this macroscopic quantity like a critical exponent. So that is called notion of the universality. Okay. Any question at this moment? Okay. And then, so what's the reason why we will get this universality and so on? So it's explained by Wilson and Ken Wilson and so on. Okay, maybe I think it's a good part. So this Curie temperature is called a second order. This is second order phase transition. Second order phase transition. So if you look at this one is very famous, right? So which one is the temperature you usually take? Temperature and the pressure, right? Let me take a look at the. Okay. So this is the pressure, and this is temperature. And usually, I don't know the detail over here, but something like this one. So this is H2O. And then here, ice, and water, and vapor. It's called vapor, right? It's a vapor. Vapor. Okay. And then around the orange temperature, we will have something like this one, right? We have orange temperature. Here you have zero temperature, 0 Celsius, and this is the 100 Celsius. Okay. And if you increase temperature, ice becomes water, and water becomes vapor. Okay, so that's, and around this time, around this point, you have so-called first order transition. So this point is called first order transition. Phase transition. So first order transition means that the some quantities become derivative become, for instance, it becomes like some quantity temperature here. And for instance, here energy is the something becomes discontinuous. I think in the case of water, it's the diagram is opposite, but the idea is that some quantity becomes discontinuous. I think something. Maybe this is free energy, and the opposite. I think in the case of the free energy. And then in the case of the water, something becomes like this. So ice to water, it becomes, first derivative becomes discontinuous. I think that's the first order phase transition. But second order is something like here. There's a famous point that if you go along this point, you cannot distinguish water and vapor. Okay? There is something, so this is called the second order, because it just becomes very continuous. It's just continuous change, but the phase will change. You cannot distinguish water and the vapor. So at this point, it's called second order phase transition. Around the second order phase transition, usually symmetry is somewhat become different, and also phase also become different continuously. So if you look at this this part, so magnetization is really the one for that captures second order transition. So here magnetization is non-zero for all temperature. Either positive or negative. If you pick positive, like a vacuum excitation value of sigma or magnetization, it just changes it breaks the Z2 symmetry. It's called Z2 symmetry, sign flip symmetry. Once you pick vacuum excitation value, once you pick vacuum excitation value of sigma, then the symmetry is broken. Z2 symmetry is broken. That is called spontaneous symmetry breaking. And if you go to the around here, even vacuum excitation value 10, it's just 0, so therefore it doesn't break the Z2 symmetry. So that is the reason why this Landau will consider the following effective theory. So if you consider the Lagrangian, it's something like where 1/2 phi minus b of phi, where b of phi is given by m by square plus lambda by the force. this should be minus sign, right? I'm not. I think I'm too stupid to distinguish Hamiltonian and Lagrange. So this should be minus sign. Okay. So then I think when m is positive. So here it's just it's called effective field theory. Some people call Lagrange model. Now in school. Since it preserves the symmetry phi goes to minus phi, it's very similar. So now here phi is a continuous variable, phi of x. So it's not discrete. So here as model everything is on lattice, but here phi takes the continuous. You just take the can be understood as a continuous limit of algebra. And then this potential is square and fold, so therefore it has this Z2 symmetry. So this is sign symmetry Z2. Okay. When m is positive, so m is positive, potential will look like this one. So this is m is positive. Okay. But once you have m is negative, so this is the m is negative. M is negative. Sorry. M is negative. Then you have some two vacuum. Okay, two vacuum. That corresponding to the magnetization. Which vacuum excitation value you will take? Okay. And once you take the one of the vacuum, the Z2 symmetry is broken. So that is called spontaneous symmetry breaking. Spontaneous symmetry breaking, and which plays a role, very important role in particle physics, whatever, like a superconductor and so on. Anyway, so that's what Landau consider as a continuous limit of the Ising model. Okay. And then I want to explain about the renormalization group flow from now, but okay, let's, and then I will explain more about why conformal field theory is important after the break. But let's take 10 or 15 minutes break, and if you have questions, tell me. And why is conformal field theory is very important in renormalization group. Juka, can you help me? Is there any way to show this? Is there any way to show this?
I think we need to open this.
And now, okay, and I think I can. Fine. Then just need to change. Okay, let's wait a few more minutes. Okay, so let's resume in that case. So this is the okay, let's resume. So this is the Ising model simulation in 2 dimensions. So you start with high temperature. It's very high temperature, summer fluctuation. So black means the black dot means the whatever up spin, and white dot means down spin. Okay, and then we start with really high temperature. So the temperature will decrease eventually, but when temperature is big, thermal fluctuation is very big. So therefore, it's very random. They behave very randomly. Okay, and then eventually temperature will decrease. Okay, now temperature. If you look at this machine, it's now decreasing. So, but still now temperature. So here is the Curie temperature. Why is Curie temperature? So, anyways, that's the case. So now the temperature is decreasing, but now still its magnetization is great. So okay, so here is almost like the Curie temperature. So therefore, some part is like a how to say, become chunk, and some part spin up, spin down, and so on. But it's like the how to say, pattern is more like a fractal. So if you could just go to this squeeze in, the pattern is really look like this. If you zoom out, zoom in, it's really like the pattern is do not change. So therefore it's invariant on a scaling transformation. And then let's go to this part more the lower temperature. So this is almost like a Curie temperature. But if you go to the lower temperature, they really become chunk. They try to align together, so align space is getting lower and lower. Become like this. So for instance, if you scale in around this point, it really become like what? Okay? Scale in around here. So therefore, it's totally behavior is totally different from previous cases. Curie temperature. So if you zoom into around this point, it becomes black, okay? Really black. Therefore, it's not conformal physics. Okay, so those are the behavior. Fine. And then, so as we go to the move on to this in this course, which is there is something, some symmetry that relate this low temperature regime and high temperature regime. So that is called Graham one identity, which we also learn because it's very important. Anyway, so that's the case. Okay, fine. And then how do you bring it up? This one?
Yeah.
Okay. So now, so let's continue to talk about this universality and also I shall look for a little bit more. So what is the idea of Wilson of this effective action, effective renormalization group? So Wilsonian effective action, action. So what Wilson considers the following. Let's consider action. Where action is okay. S of phi. Okay. S of phi. In the case of this the Lagrange model, so it's just dx and the Lagrangian, which is given by dx and half. Mu phi minus n phi squared plus lambda phi squared. Like this one. So that is the Lagrangian model and so on. Final x dx is a continuous limit of this one. So this is the action. And then the z, the partition function is given by the polarity. So this is a final path integral. Path integral. Okay. So so this integration is all possible. Integration we can consider, and so on. And what we also consider as a renormalization group is that this phi, so you just decompose as the harmonic function. The product of all k dk. I think we will calculate that previous question. At this point, I didn't see. Okay, I wrote like this. Okay, so we just have the product of k less than lambda and d write like this way e to the I. So I just went to the momentum space as lambda of the phi k. So this way of writing is that they just used, instead of here, I just use the coordinate. It's called coordinate. It's called space-time coordinate. Okay, anyway. So x is a space-time coordinate. But you can go to the, if you do the Fourier transformation, you can go to momentum exponential. And here phi k is the k which has the momentum of momentum k. And then we consider, so I just introduced so-called couple. So I only consider the field that has the momentum with absolute values less than lambda. That's the schematic way of writing path integral and momentum. The phi k is the which has momentum k, and then I consider k less than. So this is the partition function we consider, and then we just integrate it out. So here is momentum space, k whatever k1 and k2. 3, 4, no, for D, sorry, D. And then, so lambda, we start with up to, we consider lambda. So lambda is the, is also the value we consider. And integrate out all the mode which has this shell, which is lambda prime. Lambda prime. Okay. And just integrate out this field, all possible, how is it? The phi k that takes a value this thin momentum shell. Okay. So therefore, the effect, the action we consider I as lambda prime or phi is given by lambda prime, okay, lambda d phi k e to I s phi lambda. So if you integrate out, if you integrate this thin momentum shell, you get another action here. So you just integrate out all possible fields which has the momentum in this shell. So you just do that like a partial path integral. Partial means only this part. Okay, only this part. Partial. You get another action. So this is the way to go from action from S lambda, which is defined by the UV cutoff lambda to the S lambda prime by integrating out the shell. Okay. So in this way, so people just receive the coupling constant. So if action has the formula, so the S has the minus dx, and gi and OI can be anything. So in this case, in this example, OI, so O1 or X is equal to phi squared, and then G1 is equal to M. In that example, G2 is equal to lambda, or 2 of X is equal to phi 0. Okay. So that's the operator we consider. So in this way, so G of lambda, so this coupling constant, so this is called whatever called. So this is called coupling constant. And the constant receive the somehow modification by integrating out this thin shell. Okay? So you have to redefine the action when you go to the low energy by integrating out from lambda to lambda prime. Okay? So therefore this GI, so GI so this GI have something dependence of lambda. The energy scale you consider action which is defined at the energy scale, and this is called beta function. Beta function, GI. Okay. Okay. So this is so here is just a lambda delta lambda of GI, and then so the coupling constant. So the what Wilson mentioned that this coupling constant really depends on the energy, and so the coupling constant depends on energy. G depends on energy, on energy scale. Lambda, and the derivative beta function knows how it behaves under the change of energy scale. Under the change of energy scale. In the case of FIFO theory, so d equal to 1, for instance, d equal to 4, and the FIFO theory. So this beta function, beta of lambda, is given by 3 over 16 pi square lambda square. Okay. So therefore, if you go to the high energy, just the lambda will in first order application. So this is the one loop level. Okay. Therefore, beta function, if you go to the energy scale, lambda and beta or lambda is something like this. I mean, it just becomes positive. And if you go to the if you go to the lambda is increasing. So if you go to the high energy, so since it's positive, it's go to high energy. So the coupling constant increase. Okay? But if coupling constant increase, one loop appropriation is not normal about it. You have to do lots more computation to quantum correction to compute. And sometimes higher loop order will just go to the how to say, the function keep increasing or keep positive. In that case, if you go to higher energy and higher energy, the coupling constant will become bigger and bigger. Okay? So therefore, quantum field theory is essentially cannot be defined by Lagrange. But sometimes the higher loop order or sometimes non-quantum correction will change like this way. Will change like a quantum higher loop correction or non-quantum correction. Sometimes change their function to the point like this. So then it will become, and so I'm not going to go into detail. It will give you something called UV fixed point, but I'm going to talk about later. For instance, in the case of QCD, quantum chromodynamics. I think who is going to teach this gauge field theory is Guifan Chan. Who? This semester somebody will teach. You guys do not know. You guys already took this course, so there's no need to explain this one. Anyway, so Lagrange is given by essentially one of our four trace of F mu, like this way, and up to whatever. Like this way. If you include psi I should use I and maybe J, sum over J is the number quark and so on. So this is the QCD Lagrangian. QCD Lagrangian. I mean, if you want to include the QCD quark mass, you have to include the mass here. But anyway, so let's not go into detail. And then here you usually put the G square, GMS. So this GML will receive correction in the terms of energy, which is 1 to the, in this case, I mean, it depends on how many n equal to 1 to n. And if nf is equal to 0, and nf is equal to 0, 9 GQ. 16. So in this case, the beta function behaves like follows. Behave something like this, right? Beta of G is become negative. Okay. In the case of QCD, it will never happen. It will never happen to. It just go to infinity. It just beta function is the divergent quantity in QCD. But sometimes some theory can have like this way. So if you go to the beta function is what I'm talking about? Sorry. What I'm talking about. Beta function is the negative means that if you go to high energy, you become free. Okay? pretty similar. It just if you go to high energy, the coupling constant is smaller and smaller. So it become like it behaves like free period. Okay. So therefore it's called asymmetrical free period. So the QCD, if you go to high energy, you can see quark gluon, very like as a massless particle. But if you go to low energy, the coupling constant becomes huge, and you need an effective filter. So in the case of the QCD, it will never go to the conformal filter. There is a so-called mass gap. I will explain that later. It's called mass gap. So here, in this case, asymmetrical free. Free means G goes to 0, but lambda goes to 0. Lambda goes to 0. So if you infinity, sorry, this should problem. Lambda goes to infinity. If you go to lambda goes to G goes to 0. So it behaves like a GML. Okay. But if you go to low energy, lambda goes to approach to 0. G becomes really big. And you have to really consider higher loop order. In addition to that, we need to consider non-positive thing. And then if you go to low energy, people believe it to be so-called mass gap. So even though this Lagrange does not have a scale of mass, I don't introduce the mass of a quark. It creates so-called some scale. Yeah, I don't want to put some scale E. Some scale it has a dimension mass. Okay. It just creates a dimension mass. Okay. So in that case, the IR theory is no longer in conform. So there is some scale. If there is some typical scale, there is no scaling transformation you can do. The physics will change if you do the scaling transformation. Okay. However, so some cases there is something called R. Some quantum theory. Some quantum theory, so for instance, some quantum theory has a data function G is equal to T. Okay. So this is called, this is the signal that the theory is conform. Okay. This only itself means that only it's, so data function itself is just G del log G. Del G del log lambda. Okay. Therefore, this only tells that the theory is scale invariant. Scaling invariant, the invariant is different because in addition to that, you have to add the inversion. Right? So we learned that the conformal symmetry has the scaling transformation. In addition to that, you need an inversion symmetry or superconformal, special conformal symmetry. But people believe that if physics is nice physical theory, scaling invariant almost always imply conformal symmetry. Okay. There's a very nice review by Nakayama. I'm sorry, I forgot how to write. Anyway, Nakayama. I think I found it very nice actually. So it's a title review is scaling invariance versus conformal invariance. You can take a look at it about this issue. Anyway, so the important part is that if better function vanishes, which means that even quantum mechanically, the theory is conform. So if you look at that, if you look at this Lagrangian, there is no scale. So no scale, the mass dimension of G is actually 0. So F mu is given by so D equal to 4 or D equal to 4, right? So it's essentially, it depends on how you define how this F mu is often something like mu and then nu. Like this, I mean, it depends on, some people put the I here, some people put the G here, some people put the plus, and so on. But and it depends on how you define. So which means, so this has a mass dimension 1. So derivative has mass dimension what? 1. So I mean, x dot p is equal to h bar, which is equal anyway, delta x. Okay, delta x dot delta p is roughly h bar. This is dimensionless. So therefore, how to say, the coordinate has 1 over mass dimension, or the coordinate has 1 over mass dimension. Okay. So mass dimension here is minus dimension 1, because it's derivative. So this delta x is denominator, so therefore minus times minus 1 is 1. So this is 1 dimension, therefore A should have 1 dimension. Okay, mass dimension 1. So therefore this mass dimension F mu is equal to 2. Therefore this trace of F mu, so this is the operator, mass dimension is equal to 4. And if you put the action right here, so dd, so I put the d equal to 4 on the side. dd 4, x is Lagrangian here. So this has mass dimension minus 4. Okay? This has minus dimension. And then this has the dimension 4. Okay? Then counter. So therefore, which means the mass dimension of G. Mass dimension of G has to be 0. Okay? So therefore, the coupling constant is dimensionless. Okay? So therefore, classically, if you look at the Lagrangian, there is no quantity which depends on scale. Okay? Forget about, I don't put the mass here, so that's why. However, quantum mechanically, there is some correction will create the dependence of the scale. Okay? Quantum correction will create dependence on scaling. So therefore, the things are very subtle in quantum theory. But however, when this beta function vanishes, so which strongly indicates the theory is even quantum mechanically more infinite. Okay. But that's not the that's one of the and then, so for instance, if you look at that, if this kind of thing happens, so here, beta function vanishes. Okay. So G goes to 0 when lambda goes to infinity, means when lambda goes to infinity, it just goes G goes to 0. So it just lambda goes to infinity, G goes to 0. But if lambda scaling, so if there's some quantum equation that just bend this bend function to the upper side, there is something called some G star when beta function G star is equal to 0. Okay? So this one is just go to when the energy scale, if you go to UV, ultraviolet, so it's called high energy. If you have high energy beta function, G goes to 0. So that's because that's simple freedom. But if you go to low energy, which means that you go to backwards. But if you go to backwards, the coupling constant will become large. But if there is some like a non-trivial higher loop correction or non-periodic correction can bend this this curve to the upward. Then eventually it hits to the beta function beta equal to z. Okay. So this is called non-trivial fixed point. Fixed point means that when the coupling constant G takes the value here, it no longer change because the beta function is 0. So therefore, no longer if you change the scaling, no longer physics will change. Scaling okay. So therefore, this point is called non-trivial fixed point. In the case of this curve, so this is high energy. If you go to here, it's become low energy, which means. So therefore, it's called IR fixed point. IR is an infrared, means the low energy fixed point. So low energy means that so here. So the consequence of the integrating out of this high energy mode will change the coupling constant. Okay? That will give you renormalization group of the coupling constant. But if you just integrate out some big shell, whatever shell, I don't know, it depends on the theory. Some theory, so you just integrate around like this one. All the field which living here. Eventually, some theory can just reach to this point. Reach to this point. Okay? Reach to this point. Then the theory is no longer even if you integrate out the further lower energy mode, the theory won't change because the beta function is here. Okay, it's an iron fixed one. So that's the place the conformal symmetry plays a role. And then let me explain a bit more about this one. So let's see. Where is here is the So if you look at this coupling, so VDX, GI, OI, GI, OI, X, and then operator. So mass dimension of OI is equal to wait, let me take a look. Sorry. So this one has the dimension of d minus ya I. Then mass dimension of di is equal should be yi. Okay. So that's the case. Mass dimension. So this square bracket means mass dimension. Okay. And then if you linearize the renormalization group equation, so the behavior of operator of I and the x, lambda x, it behaves like a lambda yi minus d or I. Okay, so it behaves like this way. So it's just minus sign of this one. It's a minus of the scaling dimension. Therefore, GI should behave like something like a G star plus the initial condition and G0 lambda minus yi. Okay. That's how it behaves under the classical. This is classical scaling behavior. behavior. So that's how it works on the. Okay. So since dx, if you just do that x goes to lambda x, behave like lambda to the d, lambda to the d, and then what was that? dx behave like this way. Therefore, operator and this Kaplan constant should behave like a classical behave like this. Okay. So then, so therefore, when lambda becomes small, so therefore from here one can say that the y. So y is positive, yi is positive when lambda goes to very small. So if you go to low energy, it becomes relevant. It's OI. The G, this part is becomes big. This becomes this part. The total becomes big, so becomes OI is relevant. On the other hand, yi is the negative, which means that this part becomes very small. Okay. So when lambda goes to 0, this part is negligible. So when lambda goes to 0, OI becomes irrelevant. Because this part is negligible. So therefore, if initial condition is 0, if initial condition is 0, this is become negligible. Okay, then the yi is equal to 0. This is called, or I is called marginal. So this is equivalent to say that the operator dimension OI is less than when OI is the dimension greater than D, and the OI dimension is equal to D. Is y. So only the operator whose dimension is the bounded by the dimension of space-time, it becomes relevant in the infrared, low energy. Lambda goes to 0. Okay. On the other hand, the infinite many operator usually, which is greater than D. So okay, let's look at the Relevance model. Okay, Relevance model I already erased. So Relevance model potential is given by you don't like this color. I think it's less visible. Relevance model, the potential is something like this one, m phi squared plus lambda phi 04. That's the potential we look at. Okay. And then what's the dimension of phi? What's the dimension of phi? Mass dimension. So this is d minus 2 divided by 2. Okay? Is it okay? Okay, so therefore, so this pi 2 is the, therefore, phi squared is equal to d minus 2. Then is it okay so far? Pi to the fourth is equal to 2 times d minus 2. Okay. Is it okay? If these big enough, if these big like a greater than 4, this is clearly greater than d. Okay, so let's set d equal to 4. So the example that it's a much more understandable. This should be 1, this should be 2, this should be 4. Okay. 4. Okay. So therefore, this guy is the relevant. So this is the marginal. because it has the same as the dimension, but if you add phi to the k, this should be k. When k is greater than d, it's irrelevant. Okay. So the reason why I stop here is that even if you add the more whatever 5 to the 6 and so on, it's irrelevant in IR. Okay. 5 to the 6, 5 to the 8, 5 to the 10, whatever, you can add infinite many terms in Lagrange model. But in quantum mechanically, if you go to low energy, D becomes irrelevant. So you don't need to consider, because coupling constant you put here, it's G, becomes very small when if you go to the low energy. Okay? So therefore, what's relevant is very many disrelevant terms in IR. Okay? So what's relevant is, that's why it's called relevant. In infrared, low energy, it's only finite many times. Okay? That's one of the reasons why you get this universality works. If you go to IR, so if you go to the IR, microscopically, only a few terms are relevant, and the other term, you don't need to worry about it. So there are infinite many terms, irrelevant things you can add in Lagrangian, in microscopically. If you go to the low energy, which means, scale up the physics, okay? Scale up physics, those details is irrelevant. That's the meaning of the universality. Do you understand what I mean? Is that okay? Fine. So therefore, what Wilson tells us that the so what Wilson tells us that at the low energy, the people call it IR, infrared, or IR, only relevant operator matter. And you can forget about it. Irrelevant, infinitely many, irrelevant operators. Okay, so that's the notion of how to say what the Wilson's renormalization group will tell us. Okay, tells us, and that is called universality. Fine. Any question at this moment? Maybe I should keep talking. then unfortunately, right? In the case of d equal to 4, as I mentioned, lambda is equal to 0. Scaling classical scaling dimension 0. However, so as we know, beta of lambda is some number. I don't want to remember the detail. 3 over 16 pi squared lambda squared. Okay. So therefore, classically, it's classically marginal. It's a marginal. But it's not marginal. Quantum mechanics. At quantum level. So this would clearly mean that this lambda would change as you change the scale. So the Bayer function is this is computed by one loop. I think if you do the whatever, took the gauge field theory, and then somebody should tell this calculation. If the teacher is sincere and honest, this calculation is really math. So this means that quantum mechanically, this lambda receives some scaling. Classically, if you look at this one, so if y dimension y equal to 0, classically it doesn't scale. It just stays as it is. But quantum mechanically, lambda becomes increased when you go to the high energy, but the low energy is just becomes 0. Okay, so that's what's really happening. So that's very similar to the QCD coupling GM1. So it is 0, but the beta of G is still negative. So if you multiply GQ divided by 16 parts. 9 and GQ. Fine. So that's the case, the very similar case. But if you go to the some like strong decoupling behavior and so on, if you hit this point, it becomes the iron fixed point. And the beta function vanishes strongly tells us that the presence of component fixed point. And if you look at the space of coupling, if you have a free theory here, you can perturb the theory. So let's consider this a free theory. Free theory, it depends on, yes. The free theory is actually conformal. But if you do that, the deformation by adding Lagrangian, by adding this coupling constant, okay, theory is default. Okay, so the coupling constant means that in some part you can just deform the theory. So the theory like this direction or this direction, depending on which coupling constant you consider. Okay, but the most relevant part in infrared is only finite many this relevant operator. This guy. So if you only look at the low energy, the important thing is this finite many relevant term. So there are only finite many ways to go deform the theory, and depends on the theory you consider. Sometimes some beta function becomes 0, and then you get another non-trivial CFT. This point becomes CFT. So at this point, the beta function of G maybe is 0. Okay? If you flow, so this is called the renormalization group flow to the fixed point. And this part is described as CFT. From there, one can again perturb. If it is described by, anyway, if you know the operator spectrum, one can deform the theory, but there is only finite many ways to deform the theory. If you only look at the important part of physics of infrared, in only this relevant part, you can deform the theory. That's how it works. Now for CFT, it's really like some nice point, a really nice point where you can really do the analysis. So in the middle, we don't know what's going on and so on. But at the fixed point, the way is the symmetry is enhanced from Poincare to conformal symmetry. And also, if you understand this point, you know how to move the atom in space of quantum field. So this is a rough, schematic way of understanding space of quantum field theory. But at this, CFT appear a very important point in the space of quantum field theory. So that's why it's meaningful to study quantum field theory. Often, this CFT, these points are not described by Lagrange. Often, it's not described by Lagrange. So it's still very difficult to analyze. But now, there's something called which is there's something called, so nowadays it's called conformal bootstrap. Something called conformal bootstrap. Even higher dimension, many people, this is Yu Nakayama and Rich Koff, I'm sorry, I don't remember the. Anyway, many people, Rastevi, many people, so many people working on this conformal bootstrap. But even though without knowing Lagrange, so without knowing Lagrange, one can determine operator and correlation function by using conformal symmetry. So that is called operator and correlation only by using the conformal symmetry. So that is the nowadays the very become powerful technique, even higher dimension. So D is greater than 2. D equals 2 case conformal bootstrap is kind of automatic consequence of Virasoro algebra and so on. It's very straightforward to compute correlation function and so on. That is done by a long time ago. Before you guys born. Around the one anyway. So my plan is that first we learn this conformal bootstrap in D equal to 2. D equal to 2, everything is under control because of Virasoro algebra. And after that, we will go to higher dimension, and if time permits, even I'd like to talk about conformal bootstrap in higher dimension, but I'm pretty sure I will run out of time before reaching the higher dimension conformal bootstrap. But anyway, let's do one by one. I think it's okay. From next time, again, I will talk about this conformal symmetry. So I already explained what the conformal symmetry is. So QFT. So CFT is a quantum field theory with conformal symmetry. So that's one word. It's very simple. QFT with conformal symmetry. It's not classical symmetry. Okay, as I mentioned. So if you only look at the classical one, it's often misleading. Classical one, lambda and G are dimension. So the classically, it looks like it's independent of scale. Even if you do the scaling transformation classically, but if you do the computation in one loop, it often gives you some quantum correction. Okay, so therefore, we need to look at the quantum symmetry, and if you quantum symmetry is receive this conformal symmetry, the theory is called conformal field theory. And that's what we're going to learn from now. For instance, QCD is not definitely this is not a CFT in IR. So there's a mass gap. So that's a big problem. But this is not conformal field theory. Okay. But anyway, so there are lots of interesting in CFT, one can learn. But so my plan is first go to the 2-dimension. Again, in 2-dimension, as I mentioned, there's the enhancement of conformal symmetry. So first one, we learn conformal symmetry. Next time we will learn Universal algebra. Then we gradually understand this, what the operator means. What the operator means in 2-dimensional field theory, and what's the most important operator, class of most important operator called primary field. And then primary field will call, there is something called product in operator. It's called operator product expansion. From there, we try to determine correlation function in some model. It's called minimum model and so on. Some model, one can determine correlation function exactly. So there it's called conformal block and so on. So that's what we're going to learn. First, hopefully we can reach that point till around the April, or the end of April, and after that we come up to a higher dimensional field. Okay, so that's the plan. And then, yeah, so let's stop here. If you have a question, just tell me.